So now we will take some numerical example in the topic of free vibration. First, I will take an example where a system is given and it is asked for finding the natural frequency. So a diagram is given like this. There is a pulley and the pulley is pivoted at its center. This is the center, and one end of the pulley is connected by a spring to ground, and the other end of pulley, other end of the rope which is passing over the pulley is supporting a mass of weight W1, and from its static equilibrium position the displacement is taken positive downwards, and when the weight is this mass is having a downward or upward motion, the pulley is having a angular motion. Let's say theta is the angular motion of the pulley for a given displacement fraction x, and the radius of pulley is given as r. The weight of pulley is given as W2. Pulley W2. The weight of mass attached to the string is given as W1. The radius of the pulley is r, as I just said, and neglecting the slip between pulley and the spring. So there is no slip between pulley and the spring. So that is how the linear motion of the mass and the angular motion of the pulley are related to each other. We have to determine the natural frequency of the system. The spring is given a stiffness constant of K. So we'll go about solving this problem. So in this problem you see that the spring is coming on one side of the pulley and the mass is coming on the other side of the pulley. So hence the pulley is the common link. So for analyzing the complete system, we will draw free body diagram of pulley. So we will consider various forces acting on pulley. So if you see the pulley, there is one force due to the spring stiffness. There is one force due to the weight of the mass, and due to acceleration of the mass there is one force. So we will draw a free body diagram. So let's say the system is at static equilibrium position where the mass is at x is equal to 0. This is a static equilibrium position. So if x is a deflection from the static equilibrium position, the pulley will move clockwise, and this point at the pulley will come somewhere here. So there will be theta deflection of the pulley. So a portion of rope will get unwind from the pulley. That portion, the length of the rope getting unwind, will be equal to r theta. So this is radius and this theta. L is equal to r theta. Remember that we are talking about small displacement only. Whenever we are doing derivation for vibration, we are always considering small displacement, because for larger theta the things will be different. So L is equal to r theta, and since L is the unwinding taking place, so this will be L will be equal to x, the portion of rope which has unwinded. So L is equal to x equal to r theta. This is the first identity we have figured from the system. Now considering the forces on the pulley, you have the weight of the object W1, but the weight has already played its role in the static deflection. So like in the simple spring mass system, we don't consider the weight, the mg downward and kx plus delta is upward, and k delta is equal to mg. So those things get cancelled out. So static weight will not play into a role. Only the acceleration of this mass will exert a dynamic force. So if the displacement from the static equilibrium position, that is x is equal to 0, is downwards, then the acceleration will act opposite to the downward direction, because acceleration is always negative of displacement in a vibrating system, because the acceleration will always try to bring the object back to its equilibrium position. So let's say if x double dash is the acceleration, the direction of the acceleration will be opposite to the displacement. Displacement has happened downwards, so acceleration will take place towards the top side. And what will be the force due to this acceleration? Force due to the mass W1 equal to mass into acceleration, mx double dash. So mx double dash will be applied on the pulley at this point for the small deflection x due to the acceleration of mass in the opposite direction. And then since there is an extension in the spring, since this body has moved down, there will be extension in the spring. So because the acceleration is towards the top, so there will be a restoring force downwards. So F spring, since the x is top, since on the other side of the pulley the x is down, but on this side of the pulley the x is towards the top, because 180-degree shift is taking place here in the direction reversal is taking place. So since x is towards the top, the spring force will be towards the down. So spring force will be equal to kx. Now these two forces are acting in such a direction, Fs and Fw1, that they will exert a clockwise torque on the pulley. So the torque on the pulley due to weight 1, so torque W1 will be equal to Fw1 into R, and torque due to spring force will be equal to force of a spring multiplied by R. And what is the nature of the torque? This is anti-clockwise, and similarly the Ts is also acting anti-clockwise. Now these forces will cause some acceleration of the system. So since the displacement has taken in the clockwise direction, so theta has taken place in clockwise direction, and the pulley is vibrating. So the acceleration of the angular acceleration of pulley will be in a direction opposite to the displacement, to the angular displacement. So if the angular displacement is in clockwise sense, the acceleration x theta double dash will be anti-clockwise. So if you consider that force also, the torque of the pulley will be equal to the moment of inertia of the pulley multiplied by theta dash. Like you have F equal to ma. Similarly, in angular system you have torque is equal to moment of inertia multiplied by angular acceleration. So I is the moment of inertia, angular acceleration is theta double dash. So this is torque on the pulley. So the torque on the pulley will also act in the anti-clockwise sense, because the acceleration is in opposite direction to the displacement. So theta double dash is anti-clockwise. So Tp is equal to I theta double dash is also anti-clockwise. So there is no net. We have considered the acceleration of the pulley also. So now by force balance, all these forces should be equal to 0. So equating torque about pulley center, we will get Tp plus Tw1 plus T spring equal to 0. So hence you get the equation I theta double dash plus TW1 is equal to FW1 into R. FW1 is mx double dash. So mx double dash into R plus spring torque. Spring torque is Fs into R. Fs is Kx and Fs into R is Kx into R equal to 0. Now you have the identity that x is equal to R theta from the pulley, since unwrapping of theta angle will result in x displacement of the mass. So you have x double dash equal to R theta double dash and x dash equal to R theta dash. Okay. So if you substitute these values here, you get I theta double dash plus mass x double dash is R theta double dash and there is a R already existing, so you get R square plus K R x is R theta, so this one R is already existing, K R square theta is equal to 0. Now what about the mass m? We were given in the problem weight and not the mass, so your mass m is equal to weight 1 by g. Similarly, the moment of inertia is also not given. We have to make assumptions. Weight of the pulley was given, that is was equal to W2. So W2 by g will be mass of the pulley, and we have to assume a radius of gyration. We will consider the pulley, all mass is concentrated at the rim. The radius of gyration k, radius of gyration k will be equal to r. So I will be equal to WTG by r square. So if you rearrange if you write this equation better, you will get, substituting the values, you will get omega 2 by g r square theta double dash plus m is omega 1 by g r square theta double dash plus k r square theta is equal to 0. Taking the things common, r square by g omega 1 plus omega W1 plus omega theta double dash plus k theta gk theta equal to 0. So since r is not 0 and g is not 0, this expression has to be 0. So you will get W1 plus W2 theta double dash plus gk theta is equal to 0. Rearranging, you get theta dash plus gk divided by W1 plus W2 is multiplied by theta is equal to 0. So this is a second order homogeneous linear differential equation, and this is what we get for a simple harmonic motion. So the equation is x double dash plus omega square x equal to 0, and hence you get, by equating these two equations, you will get omega is equal to square root of gk divided by W1 plus W2. Like that you can get your angular natural frequency of the system. The real natural frequency of the system is 1 by 2 pi of omega, that is equal to 1 by 2 pi of gk by W1 plus W2. So this is the natural frequency of the system which was required to be determined. Frequency of system. You can notice in this case this is quite similar to the expression square root of 1 by 2 pi square root of k by m. K is there and W1 by g will be m1 and W2 by g equal to m2. So this is quite similar to k by m1 plus m2. So hence addition of the pulley has done nothing but added to the inertia of the system. But how this inertia will be added to the system will depend on how the pulley and the springs are arranged. So you have to derive the force balance by yourself and then derive the equation for motion like we have seen here, and try to compare that equation in a simplified form with the second order homogeneous equation and get omega, and from there get the natural frequency. So we have determined the natural frequency of the system, which is our answer. We'll take another numerical example in the topic of free vibration. So in this case, a very simple system is given. It looks like simple, but actually it's we cannot difficult to draw a force balance. So we'll be using the energy balance, energy conservation equation for this case. And like I told you during the derivation of theory, uh, I'll demonstrate the use of energy conservation equation for determining the equation of vibration. So here it is given that cylinder rests on a curved surface. So the cylinder is having a weight W and the radius of cylinder is R, and it rolls without slipping. There is no slipping between the surfaces of the cylinder and the curved surface. Rolls without slipping on the cylindrical surface. So the surface that where it is rolling is also given, that is a cylinder. So I have drawn at the center point here and the radius here, this line here. So if you make the focal with this center and radius, you will get this cylindrical surface. So we are on this cylindrical surface of radius R, capital R. So the radius of bigger cylinder, the cylindrical surface is R, capital R. The radius of the rolling cylinder, solid cylinder, is small r. And we are asked to determine the equation for differential equation of motion. For motion, we are going to find the differential equation for motion. And we'll consider only small oscillation. Consider small oscillation about the lowest point. So that is the equilibrium position, the lowest point. Any system tries to get to a state of minimum energy. So the lowest point here shown, which is closest to the horizontal, is the static equilibrium point. So about that equilibrium point, this cylinder is given some displacement. It will try to roll and come back to its original position, but it will overshoot and it will go to the other side, and then it will again try to come back, and the oscillating motion of the cylinder will set up. This oscillating cylinder motion is similar to the vibration. So there is a restoring force, there is a displacement, acceleration is opposite to displacement, it's trying to come to a mean position. So the theory of the vibration applies here, and we will use the knowledge that we have gained till now for solving this problem. So this problem will solve with the method of energy conservation. So for that we have to find the potential energy and the kinetic energy of the system. So we have to make some observation related to the geometry. So here let's say we have to define the displacement. So displacement we can define in terms of angle theta, that is the angular position of the rolling cylinder with respect to the center line of the cylindrical surface. So this thing can define your oscillation deflection displacement, and then theta will change when the oscillations are taking place to and forth. So, but here the thing is that there is no slipping between the rolling cylinder and the cylindrical surface. So, because of no slipping, the rolling cylinder will rotate. Rolling cylinder will rotate. So, because of rotation, it will have an extra kinetic energy due to rotation. So you could have considered a very simple example instead of this thing, that a block of solid of any shape is just slipping on the surface. Then the problem would have been much simpler. The only kinetic energy would have been the linear velocity of this component multiplied by half mv square, and the velocity would have, we could have expressed in terms of theta. X would have been r theta and v would have been r theta dash. So like that we could have determined very simply, but here the rolling is also taking place. So because of rolling, the extra kinetic energy will be there, and we have to take into account that. So for determining the kinetic energy of the rolling cylinder, we need to have the information about angular displacement of the cylinder. So let's say when the rolling cylinder is at the center of the surface at its equilibrium position, static equilibrium position, let's say the points are touching like this. So when theta degree of deflection takes place, it rolls basically in this direction and comes to this position. Due to the rolling, this surface will come in contact of the surface of the bottom cylindrical surface, and at distance will be unrolled. So this point will now be in touch. Let's say this point is P, this point is O. So at the deflection, after deflection of theta of this body, P will be in touch. So what, and O will come somewhere here after this rotation, because rolling is taking place. This is a clockwise rotation. So what is the distance OP? What is the distance OP? If you zoom in here and if you draw an angle xi of the rotation of the cylinder, then distance OP will be equal to r xi. Now this rolling has happened without any slipping, so that this distance here from O1P to the final OP, this distance should also be same as what is what has been in touch with this smaller cylinder. So O1P will be equal to OP. And what will be O1P? From the geometry of this circle, the bigger circle with radius r, you can see O1P will be equal to r theta. So hence you will get r theta is equal to r phi, r phi. So this is nothing but just from the consideration of the surface. After rolling, it has reached somewhere, so the distance traveled on the both the surfaces would be same. So the distance traveled on the cylindrical surface, the base surface, is O1P, and the distance traveled on the rolling cylinder is OP, and both the distances should be same. So that's why this condition is coming, and you get the identity like this. R and smaller and bigger are known quantities, so you get the relation between xi, which is angular displacement of rolling cylinder about its own axis, and theta is angular displacement of rolling cylinder about the cylindrical surface center, cylindrical surface axis. So we have found a relation between these two. Now the motion of the rolling cylinder can be decomposed into two parts. One is the translation of its center. So there is a translational motion of center, and other is rotational motion, pure rotational motion. So the translational motion of the center, the displacement, translational displacement will be given by theta multiplied by this distance from the center of the cylinder to the center of the cylindrical surface, that is equal to r plus rotational displacement. Rotational displacement, this rolling cylinder has done an angular displacement of xi. Also, it has done an angular displacement of theta in this direction. this direction. So when you look this circle, the theta displacement comes in the opposite direction. So it has done a motion of theta anti-clockwise and xi clockwise. So the rotational displacement is equal to xi minus theta. This minus theta is coming basically from the funda that we've already considered the effect of the angle theta in the linear displacement. Hence, this motion has to be subtracted from the rotational displacement. So, what is the linear velocity of the cylinder? Linear velocity will be equal to theta dash r plus r. So, differentiation of displacement dx by dt. Similarly, the angular velocity will be the differentiation of the angular displacement, that will be equal to xi dash minus theta dash. D xi by dt minus d theta by dt is the angular velocity formula. So, what is the, we substitute our identity here. R theta is equal to r xi. So xi is equal to capital R theta by small r. So hence you get angular velocity is equal to r theta dash by small r minus theta dash, which is equal to r by small r minus 1 theta dash. So what is the kinetic energy? Now we know the velocities of the rotating cylinder. The kinetic energy will be equal to linear kinetic energy plus rotational kinetic energy. So the linear kinetic energy is equal to half mv square total Ke. So linear is half mv square, half into m into velocity, that is theta dash r minus theta dash square r minus r whole square plus the rotational kinetic energy, that is equal to half I omega square. I, the moment of inertia we have to take for the disk. We know that the rotating cylinder is a disk. So we will take this formula for the disk. The moment of inertia for a disk is I equal to r square by 2. So this is for the small cylinder, the current rotation kinetic energy. This is equal to I m square by 2, and the angular velocity is r by small r minus 1 theta dash. So we'll have a whole square of that. So half I omega square. I omega square. And if you simplify this expression, take the common things out, you will get half m theta dash square out, and you can take maybe r minus r whole square also out, and here you will have r minus r by small r whole square. So here you have a r square in the numerator, you will have r square in the numerator, those both will cancel out, and r minus small r is taken common outside. So if you see this expression, you will get a 1 here, and you will get plus 1 by 4. Sorry, the 1 by 2 is taken out, so you get a 1 by 2 here. This will be equal to 3 by 2, and 3 by 2 plus 1 by 2 is equal to 3 by 4 m theta dash square r minus small r whole square. So this is the Ke of the system of the rotating cylinder. What are the potential energy? The potential energy in this system is due to the gravitational potential energy. So you have the cylinder sitting at the equilibrium position. This is a deflected position, and the center has moved to some height, this h, due to the angular displacement theta about the center of the cylindrical surface. This is theta. So what is this height h? If you draw this line and you get a perpendicular on the initial line, the equilibrium position line, and you have the radius equal to r from the center, then this distance, center to center distance, is r minus r. So in this triangle, if you see, you have this r minus r distance, theta 90 degree, and then r minus r distance again. So the height h will be equal to r minus r minus r minus r cos theta. So this distance from here to here will be r minus r cos theta, and complete distance is r minus r. So hence h will be equal to this value. So we know that the potential energy is equal to mgh, weight into the height in the against the gravity direction. So we will get mg, and h is r minus r, will take common outside, 1 minus cos theta. So this is the potential energy of the cylinder.